Okay, so the first example, which is sample problem 321, is taken from GL Medium book. So in this case, a particle with a mass 0.5 kilogram has a velocity of 10 meter per second in the x direction at time t equals 0. Forces F1 and F2 acts on the particle, as you can see in this figure here, and the magnitude changes with time according to the graphical schedule shown. So this is the graphical schedule according to which these forces are changing with respect to time. So these are forces are in the y direction and times is in the x direction. F1 is changing this way and F2 is changing this way. So determine the velocity v2 of the particle at the end of 3-second interval. So you have to calculate the velocity of the particle after 3 seconds, and the motion occur in the horizontal xy plane. So so the motion is happening in xy plane here. Okay, so to solve this problem, okay, first you know the mass is given, which is 0.5 kilogram, and the v1, which is given in the x direction, which is 10 meter per second. So this is v1x, and v1y is 0 here. And you are given the forces according to this graphical representation, and time interval is from 0 to 3 second. So 3 second is the time here, and what we need to calculate is v2, which is the final velocity here. So obviously we will need to calculate v2x, and we will need to calculate v2y. So you have to calculate both uh, component of the velocity, or in another word, you will need to calculate v2, which is is a vector, and then you will need to calculate the associated angle with the x-axis, for example. Okay, so as you can see in this figure here, that you are given velocities, and you are given time, you are given the forces, and you are asked to calculate the final velocities. So as we discussed earlier, in this specific case, it's always straightforward to use the impulse momentum diagram, or impulse momentum principle. So we will start with the impulse. Okay, so impulse momentum principle is that g1 plus impulse, which is the integration of forces from time t1 to t2, and f dt equal to g2. So this is the impulse momentum principle here, which we can represent in the graphical form. So if you consider this particle here, so we will consider the particle. And as you can see on this particle, we have initially it's the g1. So g1 means that the particle should have the momentum at point 1, which is g1, and obviously this g1 is a vector, so which we can split into two components, g1x and g1y. So if you do that, so the g1 x will become mv1x, and this will become mv1y here, and then plus the impulse. So the impulse in this case is the forces applied on the particle, so which is this term here. So as you can see, there are these two forces. So one will be in this direction, so which will be uh, t1 to t2, and then f2 dt, and then another impulse will be in this direction, which will be again from t1 to t2, and f1 dt here. And then finally what we will have our uh, final final momentum, which is G2. And G2 again, we will split this into two component, into the X and Y component. So X component will be in this direction here, and Y component will be in this direction here. So mv2x and mv2y. Now, because we don't know the final velocity, so we are assuming that the final velocity is positive, as you can see here. So the final velocity in x direction is positive, and the final velocity in y direction is positive. And if you draw the x and y coordinate system, so it will be more easy to then understand everything. So here we are assuming that the x direction is in this direction here, and the final momentum in the x direction is positive, and the final momentum in the y direction is positive. This is our assumption because we don't know the velocity here. So if we get the from the calculation, if we get the v2x is negative, so this means that the assumed direction was wrong, and then it should be the other way around. And if we get a positive answer, so this means that the assumed direction was correct. Okay, so now from this diagram, now we can write two equations, one in the x direction, one in the y direction. So as you can see here, in the x direction, we have mv1x, and as you know that you are given v1x, which is 10, you are given m, which is mass, which is given, which is 0.5. So what we can write here is uh, 0.5 times. So this is what we are writing now, equation in x direction. So 0.5 times 10, which is the mv. So mv1x is 0.5 times 10. And then as you can see in x direction, the applied force is in the negative x direction. So this means that the impulse is negative. So that's why we should write it as negative. And if you look at this equation here, it is the integration of force with respect to time. So this means that this F1 is given is this force here. And if you integrate this F with respect to time, what you will get? You will get this area under the curve. So you will just, if you look at this figure here, and if you take this F1, which is changing this way, so if you integrate this force F1, so if integrate, so this area under the curve is just this is our time, and this is our force. So this area under the curve is just from 0 to 3. So the time here is from 0 to 3, and then f dt. So if you integrate this force with respect to time, you will get this area under the curve. In this case, you even don't need to do the integration. You will just calculate this area under the curve in this case of the F1. So as you can see, it is just two rectangles. One is this rectangle here, which is from 0 to 1, and one is from 1 to 3. So you will just calculate these two areas, and this will give you the area under the curve, so which is straightforward in this specific case. So if you calculate this this area for the first area here, which is this part here. So for this part, the x-axis is from 0 to 1, and the y-axis is 4. So the area will be 4 times 1. And then for the next part here, which is this this part here, the green one. So it is from 1 to 3. So this is mean this is 2, and the y is 2 here. This means that it should be 2 into 2. So it's just the area of these two rectangles. And then on the right hand side, we have the G2, which is in the x direction. So mv2x, so which will become 0.5 times v2x. Now in this equation, it's just a straightforward equation from which you can calculate v2x straightforwardly. So v2x will become equal to minus 6 meter per second. And now this is very important to know that you get negative here. So our initial assumed direction was was in this direction, we assume that the acceleration, the velocity will be positive here, and it should be in the positive x direction. But from the calculation, what we get was a negative answer. So this means that the actual velocity is in the is to the left. So it's in the opposite direction to the one that we assumed here. So this is just to make sure that you know what this negative means. And the units is again important. So this is the meter per second. Okay, now this was the velocity in x direction, but obviously you are also applying a force in the y direction, so the body should also move in the y direction. So now you need to calculate the velocity of the body in the y direction, which you can again use this impulse momentum diagram, and you will now take the y component in this specific case. So if we now take the calculation in y direction here. So in y direction, as you can see, you have this mv1y, but again, because this v1y, which is the initial velocity in the y direction, is 0. So if it is 0, this means that the initial momentum in the y direction is 0. So this means that in the y direction, the initial momentum is 0. And then we have the momentum of the force in the y direction. So in this case, again, you are integrating this force F2 in the y direction from T1 to T2, which is from 0 to 3. And as you can see from this figure here, that this was our force 2. So it's going from 1 to 2, and then it's going something like this. And again, this is 3, and this is 1, and this is time, and this is force, and this is 2 here, and this is 3 here. So again, if you look at this case here, you can say that you can split this maybe in 3 parts. So just one is this area here, and then you can calculate this area here, and then you can calculate this area here. You can just spread this into 3 parts, or maybe 2 parts. So one, this big rectangle here, and then this triangle here. So this area under the curve, which is this impulse T1 to T2 F2 dt, is just area under this curve here. So just to show that this area under the curve is T1 to T2 F2 dt. So if we just take in this case here, so as you can see that F2 is acting in the positive y direction. So in the previous case, because F1 was in the negative direction, so it was negative, but F2 is in the positive y direction, so it should be positive here. So therefore we are writing here a positive here, and then area under the curve. So one is the area of this black triangle, which is 1 into 2, and then the area of this this small triangle here, so which is from 2 to 3, which is 1 is here and 1 is here. So again, it's gonna be 1 by 1. And then again, the area of this triangle here, so you know the area of triangle, which is half the area of triangle here is half b into h. So b is the base and h is the height here. So in this case, what you can do is this become half, and the base here is from here to here, so which is 1, and the height is from here to here, so from 1 to 3, which become 2. So this is the impulse, which was the integration of the force with respect to time from 0 to 3. And then on the right hand side, what we have is the final momentum in the y direction, so which is mv2y, and we know the mass which is not changing, so it will be v2, mass times velocity in the y direction, so v2y. Now in this equation, the only unknown is v2y. If you do the calculation, you will get v2y, which will become equal to 8 meter per second, and this will be a positive value. So this means that that the assumed direction, which we assume that the body is moving in this direction, so which was correct because we get a positive value. So in this case now, because we have the velocity, which is the final velocity, and the final velocity obviously is a vector, and which consists of two components. So one is the uh, is the component of this velocity in the x direction. So you write this in this form, that minus 6i, and I is the unit vector in the x direction here. And then you have 8j. So 8 is the this 8 here, which is the component of velocity in the y direction. And then you calculate this j is the unit vector in the y direction. So now from here you can calculate the magnitude of the velocity, which will become v2, and which will become just 6 square plus 8 square under the root by using the Pythagoras theorem, and that will become 10 meter per second. And similarly, you can also calculate the angle. So in this case, as you know that uh, it will be always good idea to draw where the velocity is going here. So as you can see in this case, the x is negative, so you are going from here to here. So it is minus 6, and then the y is positive. So the y component is in this direction here, 8. So the final velocity v2 is in this direction here. So this is our v2, and this was v2x, and this was v2y. So this means that the final velocity is in the second quadrant here, because the x is negative and the y is positive. And you can also calculate the angle here. So if you can use this theta x with the y with the x-axis, so tangent inverse, and minus 6 by 8, so you will get the angle will become 126.9 degrees here. So this is how we can calculate the final velocity. And because the final velocity is vector, so you need to calculate its magnitude and also its direction.